But that's another real benefit to using that. Broadcasting is another one that's a bit tricky. If you run into an odd scenario where all of a sudden, like your Python code is giving you a completely weirdo result, 9 times out of 10, in my experience, I've messed something up with broadcasting rules. So just be aware that when you are deploying functions to NumPy objects, be they lists or matrices or vectors or whatnot, generally speaking, it'll work the way that you think, but you might want to like print out the result and just to make sure that it's the right shape, right? Because sometimes you get a completely weirdo shape. And second of all, like you realize that, okay, it's doing something completely different. It's another funny one. Okay, I'm just gonna close this source. Okay, so linear systems. The goal, you can see I'm trying to like revise my lesson plans as I go. So this is one of the big things. The goal of this particular section is to write down linear systems, and first of all, write them down. Second of all, write them down in matrix form. We're going to look at the solutions using graphical elimination and matrix methods. And there are pros and cons. Personally, when I see something in the graph, sometimes it clicks. Sometimes the elimination method works. So I'm, universal design and learning techniques to show the different ones, and whatever clicks, that's, you go with that. That will help us understand why solutions exist and why they don't, or why they're infinity. Everything is a solution. And then we're going to look at some methods to quantify all this. And that goes into the condition number and the determinant of the matrices. Yeah. This is, I'm hemming and I was hemming and hawing and kind of struggling with this lesson too, because some of the techniques that like I'm going to be covering now are a little bit limited in that's not always the way that like NumPy will actually do these things. The problem is that if I go into the way that it actually works, then it's kind of like it's beyond 30, or frankly, it's into graduate studies. So I'm gonna hit you right off the bat, and then I'll simplify it down. Not simplify, make it accessible. Right? Like sometimes you need to have a bite-sized piece of information before you can expand, but then I'll show you the direction that it expands afterwards. So linear system solvers are the workhorse of scientific computing. They're literally all over the place. They include the canonical solve. So if you have AX equals B, X equals B over A, technically that's a linear system that you just solved, right? In contrast, X squared equals 1, that's a nonlinear system. So one thing that you note is that you don't have a single answer to that one. You have multiple answers. And that right there is a very key point there. In general, we're going to have n unknowns, and they have to be solved simultaneously. So you're going to have to find a single set of X, Y, Z that satisfies all of the problems that you've defined. The group, and so sorry. So here's already where I've generalized it, and then I'm going to have to bring it back down. So we're going to have n unknowns, and we're going to have m linear equations, right? And then what you do is you put it together into this kind of standard linear form, ax is equal to b, where A is called the coefficient matrix. That can be of dimension n by m. X is your unknowns, so your n unknowns, m by n, sorry. M by n, X is your unknowns, and then B is your constants, and that's where you have the data points, the M data points. Generally speaking, in this course, I'm already questioning this one. Generally speaking, in this course, we're going to have n equations and n unknowns. In general, for example, we're going to be talking about curve fitting and linear regression and things like that. The way that you do it normally is, so what that means when you have a curve fit, for example, you have like 2 equations, right? You have two pieces of 2 variables. So your n is equal to 2, but you have 100,000 data points, right? So your equation, your A matrix, is actually going to be M 100,000 by 2. And then you have your X, and then you have your 100,000 data points, right? So you actually get a rectangular matrix. And you can actually find the inverse of that using something called the pseudo-inverse. We might touch that in the polynomial fitting, in the regression section. I'm not sure yet. The previous courses haven't used that technique, but that is kind of the norm. So that's like when you're going to be using NumPy and things like that, that's actually what it's doing. It's using the pseudo-inverse concept. So here's what I'm saying. In general, you can think of A as a square matrix, n by n. We might expand that a little bit later. And actually, there's a brain teaser at the back here, the bottom here. Okay, so demonstrative example. We're going to be coming back to this one again and again and again. Organizing a fundraising event and you need to buy tables and chairs. Chairs cost $20 each and the table costs $50. You have a budget of $700. You need a total of 20 pieces of furniture for some reason. Who cares? It's a problem. Chairs and tables combined. How many chairs and tables should you buy? So if you spend like a couple minutes staring at this problem, it's a pretty easy answer. But we always have to write out the problem. That's honestly, like, if you're ever stuck on a problem, first thing to do is write it out. So the two equations here, I know they're on the board. Ignore the board for a second. Anybody tell me what the equations are? Yes, right? Super easy. So you put that down into your equations. Here are your equations. What geometric object do these equations describe? Equation with two variables defines a what? A linear system, yes. First word, first four letters. Line, right? Which is where it comes from, right? Not by coincidence. So let's plot the line. Right, this is the Gemini. Yes, run anyway. This is the Gemini. Here's my prompt for plotting this. Thinking. Here are the lines. Right. So this is, by the way, the instruction from last time was all about like the different commands and the syntax for Matplotlib. Gemini, ChatGPT, like it just simplifies this stuff so much. But like, and it's pretty readable too. So if you did have to go back and you had to figure out, well, I want to add in the units to the label. Well, obviously it's going to be plot.x label is the X label. That's a benefit of Python. So here are the lines. Somebody tell me the solution. You got it. Super easy, right? Each line defines one of those relationships. Where they coincide is whatever satisfies both of those relationships. Point of generality. If we had a 3x3 system, 3 unknowns, 3 equations, that would be geometry object. What's 3 variables defined? Yeah, but actually that one would be a plane. Yeah. So with the 3 variables, you get a plane. You have 3 equations. So you're going to have 1, 2, 3. A point of intersection is a point. Literally the point of intersection, right? If you have 4 equations, you have a, technically it's a volume. Everybody else would say hypersurface, and that becomes your nth dimensional like intersection n minus 1 dimension. But it just follows, right? Like the more equations you have, it's the point of intersection, basic geometry, you have a single point. Good. Problem with that is that you can't see. So, and it kind of becomes hard to work with, but that's the idea behind it. Okay. How many solutions are there to this problem? Obviously, right? Are these lines ever going to meet anywhere else? No. Okay. So we have just proved uniqueness, by the way. So we can also just kind of stare at this and use our mighty human minds to figure out, like, just do this by elimination, right? Especially the second line, c plus t equals 20. C is equal to 20 minus t, plug that in, and substitute the answer, and we get 10 and 10. Again, not complicated. This is actually the basis of all of the matrix manipulation that we're going to be doing later. But let's not talk about that one just yet. Actually, no, sorry. Let's talk about it right now. So formalizing this method, putting it into the matrix, we get this matrix 2050 11. Your unknown variable here is CT, and the constants are 720. Does this equation make sense to everybody? Or should I, yeah. Oh, I forgot. Oh, yeah. It actually works. That's why I left it. That's why I left it. All right, okay. No. It's okay. Do you guys want me to write it out? No. No, yeah, get it. Right? All you do is, do I assume correctly you guys know how to like matrix multiplication, right? Yeah. Anybody who doesn't, and like, is a bit shy to say anything, just send me an email or come to my office, and like, it's no problem. Okay. So what we get is 20 times C, 50 times T equals 700. That's your first equation. 1 times C plus 1 times T equals 20. That's your second equation. Great. Do you guys remember, actually, we don't need to do that. Let's do the matrix inverse. So next lecture, we're going to talk about Gaussian elimination. That's the whole thing where we're swapping rows and we're multiplying different rows. How well do you guys remember that one? Yeah. So what we're going to do is we're going to go back through that. We're going to review it, and then we're going to make it computational so that we can get the computer to do that for us. And then we're going to forget it and have the package do it for us much better than we can. So matrix inverse. The idea is that if you have AX equals B, right? X and B are vectors. A is a matrix. Let's find the inverse of A such that X is equal to A inverse B. Great. For a 2x2 matrix, the inverse is formulaic. Actually, they're all formulaic, but formulas get horrendous, really terrible, right? But what you get is this expression. You have 1 over the determinant. That's a key quantity. We're going to keep coming back to this one. This second matrix is called the cofactors or adjugate matrix. Don't need to know that. The key point there is that you have the 1 over the determinant. And the determinant of the matrix for a 2x2 is given by this funny equation. 3x3 and up, there are different measures of how to calculate this thing. I'm not sure why that didn't render. Excuse me a second. There we go. So this prefactor is systemic to inversion. Wherever you do inversion, you're going to get this prefactor hanging out there, regardless of the technique that you're going to use. One inverse is as good as another. Because it exists in one, it's going to be built in to all of the other ones. Okay. For our case, determinant of our A matrix is minus 30, and we calculate the inverse, which is this, and multiply through, and we get 10 and 10. Great. We're done. Let's tweak our problem a little bit and see what happens. There's a sale on tables that goes down to $20 each. The customer heard about it and cut our budget to $400. So our problem is now 2020, 400, 120. Does anybody see a problem with this? Right off the bat. It's the same equation, right? In general, once you get like a lot of different equations and unknowns, that doesn't become so easy to see, obviously, right? So we already know that we're going to have a problem. So let's plot it and see what it looks like. It's the same equation. It's the same line. So what does this mean? Yes, there is always a solution for the number of tables and chairs. And because we're mathematics and we're divorced from reality, we can have negative numbers of chairs and tables. And it still works out. What's that? Minus 100,000 plus 100,000 and 20, right? Okay, so when we try elimination, right, what we're going to get is the same equation. We plug those in and we get good old 0 equals 0, which is trivial and not very useful or informative. So what that means is that, yes, in fact, we have an infinity of solutions, and any set of C, for any C, there's a corresponding T for which this is satisfied. When we look at the matrix equation, we see that the determinant is 0, right? And the determinant is also related to the volume of the object that all the rows in the matrix makes when they're multiplied together. There are other ways to think about that too, and why this makes sense, but we're not going to talk about that one. That's a little bit mathematical. So if the determinant is 0, what does that mean for the inverse? Not invertible. What actually happens when you go and calculate the inverse, though? It approaches infinity. You got 1 over 0, goes off to infinity, and everything dies. Okay. Tweak number 2. Whoops. Customer meant to say $500. No more and no less. Exactly $500. Don't give anything back. Anybody have a guess? I heard it. Solution. Graphically. By the way, I love that I can give like AI a prompt. Graph it again, please. And it'll actually do it. Here is the result, right? How many places do these two parallel lines intersect? Necessarily. If they are parallel planes, 0. If they are whatever hypersurfaces, 0, always, right? So that means, yeah, there isn't a solution at all. These equations are, I think I come back to those ones. Okay. And when we go to through elimination, what we're actually going to find is 0 equals 100. And it's not. And the method is wrong. What happened to the determinant? Anybody? It didn't become 0. It's still 0. Right? Just by changing the price, the total budget from 400 to 500 didn't do anything to the matrix, right? We still had the individual prices of the chairs and tables, and it didn't change that. And that's kind of important because that means the invertibility of the system A doesn't matter on B, right? It's a property of the matrix itself, not the constant on the other side. So what this means, putting it together, is for linear equations, which is equations in 2 unknowns, or excuse me, linear equations in 2 unknowns are lines, right? The solution is the intersection, and the lines can either intersect in one place, every place, or no places at all. For 2 and 3, the lines are parallel, right? So this is a property of the matrix itself, matrix A. What that means is that you can slide one on top of each other, but it means that they're linearly dependent, right? Linearly dependent means that you can just take one of the lines, you shift it over a little bit, and it falls on top of the other one. It also means that you can't invert it, regardless of what you put for your constant vector B, right? Example 1 is linearly independent, only intersect in one place, and they can be solved. So scenarios 1 and 2 are solvable, in that they do have a solution. Scenario 2 is that they have all solutions, but it is still a solution technically, right? So those are called consistent. And the other one is inconsistent because there are 0 solutions. What that means for the coefficient matrix is, first of all, that A depends on the nature of the lines.
Gary did about as good a job as you could expect guarding my phone.
Somebody talking to me?
No. We gotta. Somebody's mic is on.
Mute. Ariane, we heard you. Turn off the game. I don't know if I can be like summoned for a tribunal for like mute shaming. That should totally be a thing though. All right. So the coefficient, yeah. So the coefficient matrix A depends on the nature of the lines, not the constants, right? When the determinant is equal to 0, it is non-invertible. Fine. That's called singular. by the way. Singular matrix, not invertible. This is problematic. And you should be scratching your head a little bit about this, right? We have, there is presumably some relationship between the determinant of the matrix and the ability to solve it, right? Let's do first order approximation, which means everything is aligned because we're engineers, everything is aligned, right? And we have two data points here. When the determinant is 0, fail. When the determinant is minus 30, works, right? So this is kind of a weird behavior. Usually you would expect things to be kind of a smooth sliding scale, not, you know, a heavy side function here, right? You guys call it heavy side function or step function? Heavy side? Both? Yeah. Same thing, right? So it kind of begs the question. First of all, what's the significance of minus 30? Somebody take a guess what the significance of minus 30 is. It's not a 0. Yes, right? But the actual value, right? Like minus 100,000, positive 100,000 is also not a 0, right? So why minus 30 and not anything else? And actually kind of obviously, right? Like it is arbitrary. Its only value is that it's not 0, almost. So works, doesn't work. What's happening in between? Right? If you had minus 5, would that work? Okay. If you had minus 5e minus 10, would that work? 0.00000005, would that work? Maybe, right? What's that? Yeah, if you did it by hand, yes, yeah, exactly. So you already read it. You already read the notes. Right? All this, all of a sudden, like all this is kind of tying back to what we talked about last week, right? So let's do this analytically. Let's say that the table, so we have, let's focus on the 0 case, right? So $20 for chairs, $20 for tables, problem not working. So let's say that the tables actually cost 20 plus epsilon. Actually, I said 20 minus epsilon so that the negatives cancel out in the determinant and just makes things a bit easier. Okay, so the tables now cost 20 minus epsilon. We work out the determinant and we get that that's equal to epsilon. Great, convenient, right? The inverse equation, when we go to calculate that, that prefactor now goes to 0. So all of a sudden, this kind of makes sense, right? Like what's happening when that determinant goes to 0. When we look at, what did I do here? Right. So let's look at this graphically, okay? We look at an equation like this. My personal notation, by the way, I like to use square brackets when I'm grouping terms. And I like to use, which ones are these? Parentheses? You can never keep them straight. I like to use the round brackets for function arguments. So when you see the square brackets here, that means we're grouping terms. It's not a function. It just keeps things a bit cleaner when we start to mix everything together. Let's look at plots for different values of epsilon. So this is going to be minus 30, minus 10, minus 1, and 0. And sure enough, what we see is C plus T, our nice original blue line, is here. For epsilon minus 30, that's a purple line, there is 1 point of intersection. For epsilon minus 10, how many points of intersection? 1, right? For epsilon minus 1, how many points of intersection are they? No, 1. It's just, it's off screen, right? But like we could tweak the, if I do this, then you don't get to see any of the other ones, right? And it just kind of gets lost in the figure. But yeah, there's still 1, right? For, put that back so we can actually see something. For epsilon, well, let's do a live demo. For epsilon being 0.001, how many points of intersection are You know what, actually, my Wi-Fi has a strong signal. Oh, there we go. We're back online? Okay. So my Wi-Fi actually had a strong signal that whole time. I don't know if that was like Teams snafu or what. The Teams meeting, by the way, I paid a little bit extra and I got the call-in numbers. So if anybody is like remote connecting from somewhere with poor internet, what we used to do at Canadian Nuclear Laboratories, because we were in the middle of nowhere, is we would have a video call on our computer muted, and then we would be calling in from the landline. So that like even if the video died, or like sometimes if people were on really poor connection, everybody had to shut off the video, then you still like get your audio. So if you are remote connecting and you're doing it from the road or something like that, and you have it on speakerphone, use the call-in number. It's a cell, normal voice line, and that's at the bottom of the Teams invite. Okay, so for any epsilon greater than 0 or less than 0, frankly, right? How many? Oh, sorry, I shouldn't have spoiled that one. For any epsilon greater than 0, how many points of intersection are there? For any epsilon less than 0, what happens? Right? Curves the other way. Line slopes the other way. Now you get a solution over there. So a solution does exist, but those lines are getting more and more and more and more and more parallel. And when those lines get more and more parallel, we're going to have more issues resolving where they actually touch. Just like, like this, right? Like we can't even see it. We can't even read off the solution because the thickness of the lines, right? What that means numerically is that we're going to get what kind of error? Round off error. So when we do the substitution, what we end up finding is T is 300 over epsilon. Here are some examples of epsilon versus the solutions, right? For 30, you get 10 minus 10 is there. Can you guys read this? Is this like too small or something? Yeah, okay. Right? And like once you get down here, you get like 0.1 and your solutions are up in the thousands. When you get way down here, you get like 10 to the like molar quantities of these things. And what happens when you start mixing magnitudes? You're signing your own death warrant. Like the numerics just always you'll have round off. Like 10 to the minus 20, or yeah, 10 to the minus 20 is the round off error that we were talking about in floating point precision, right? But if you try and do that here, all of a sudden your 0.03 becomes 0.030000000025. And that 25 dominates your entire solution, which is bad. Don't want that. So what we want to do is we want to quantify this. So we return to the importance of minus 30, which obviously isn't anything. That minus 30 is only significant with relation to the other terms in your matrix, right? When we do the inverse, we're going to do 1 over determinant times that cofactor. That cofactor is actually a very complicated process to work that out. Never do it symbolic. Never, ever, ever. I made that mistake once. I had to shut down my computer because it was still chewing. Only do it numerically. For anything like bigger than a matrix of 3, even 4 is pushing it. Because you just get like all these terms piling up and it just becomes a giant mess. Right? So with that matrix, I'm just going to go back to it here. Eventually, where is it? There we go. Right? You have 1 over the determinant and then the elements of the matrix. So it's not really a surprise that the magnitude of your determinant only really has relevance to the elements, the magnitude of the elements of your matrix, or more condensedly, the magnitude of your matrix, right? And then people start to say, well, what the hell does that mean, right? Like, what's the magnitude of a matrix? Fortunately, we have it. It's called norms, right? So what is the magnitude of a line? Actual question. An actual line, like here to there. Yeah, it's just a line, right? Numerically, what we have to do that is we do the square root. I mean, this is Pythagoras, right? right back to Pythagorean mathematics. We do the dot product and then the square root. Wouldn't it be nice if we can do the same thing for a matrix and thereby get an understanding of the magnitude of that matrix? Matrix norms are not all equivalent. By the way, I might come back to this one and expand a little bit on the different types of vector norms. There are also different vector norms. The easiest one that we're all familiar with is the Euclidean norm, which is Pythagoras, right? The other ones, so the generalization of that, it's called the P norms. And P can be any integer. And the way you calculate that, technically is infinity is an integer, right? I don't know. It can also be infinity. Whether or not infinity is an integer, I'm not actually sure. Right? So the way you calculate that is that you take all of your vector elements, you raise it to a power, you sum them all, and then you take that power root. So your P3 norm is a cubed plus b cubed plus c cubed, sum them all together, and you take the cubed root. What do you think happens when you do the infinite norm? You don't get infinity. You have to do a limit. Which is worse, right? When just making the big bigger. So when you do the infinite norm, you're taking your max. You're taking your maximum value. And that's kind of useful because later on when we go to time steppers, right? What we're going to do is we're going to be representing the solution to our problem as a vector. Spoiler alert. It's going to be a vector. And then we're going to change it from one time step to the next. Well, there's a question. How do you tell how much your solution has changed? One way is to take the vector is to take the norm of those two differences, right? Vector difference, you take the norm, is that too big? Another way is to look at those two vectors and say, what is the maximum change, right? And that has different time stepping properties. Not so much convergence, but sometimes you can get faster. It kind of depends on the problem. So I might end up coming back to vector norms, but that's a big aside in this context. So there are also matrix norms. There are a few different ways to calculate it. The Euclidean / Frobenius norm is basically the extension of the Euclidean vector norm. So it's Pythagoras applied to matrices. So what you do is you have your big matrix, 1, 1, 1, 2, 1, 3. You multiply those two elements, you square them, right? You sum up all of the elements in your matrix, and then you take the square root. So what you're basically doing is you're kind of picking out, well, in the infinite extension to that, you picked out your maximum matrix element, right? Which isn't actually so helpful sometimes because matrices are more complicated for this context. Anybody ever seen this symbol before? Double dot product between matrices? I think so. Okay, it's a little bit exotic. It's like the dot product for a vector, but double dot means that you're multiplying everything element by element, and then you sum everything on the other side. So imagine dot product for that. There's also the row sum norm. I don't. Oh, not again. All right, stop making that noise. What you're doing there is you're taking the sum of each row of your matrix, and then you're taking the maximum value of that. Right, and now we're starting to like touch on what matrices actually are doing and how we're transforming basis vectors, and then we're taking the maximum of that. Okay, there is also something called the spectral norm, and that's the maximum eigenvalue of your matrix. And that's actually kind of a useful one. That's probably one of the more useful ones. But that requires eigenvalue decomposition that we won't get to until later in the year. We will actually get to that. Okay. The determinant is considered small in comparison to the norm. And because you have different different ways to calculate your matrix norm. You have different ways to ascertain whether or not it's small. Generally speaking, all of your norms are kind of similar order of magnitude. So you don't have to worry about it too much. Find one that calculates quickly, and you can look at that. Let's see. Oops, shouldn't have this line here. There is a formalized concept called the condition number. The matrix condition number is the ratio, is the product of the norm of the matrix and the norm of the inverse of the matrix. Right? Which is a little bit strange, right? Because that kind of implies that you're calculating the inverse of the matrix before you know whether or not you should calculate the inverse of the matrix. But ignoring that fact for a minute, that's kind of like the normal way that you would say. And then for a condition number to be close to 1 is good. Anything above or below 1, and you're kind of in risky territory. There is a rule of thumb out there that's I think for every order of magnitude on your condition number, not important, just giving it to you guys for context. For every order of magnitude of your condition number, you're going to lose 1 decimal worth of precision. That's kind of that's the rule of thumb. But basically the whole idea, you want your condition number to be roughly 1. So the nice thing about this condition number and the counterpoint to me saying, you're calculating the inverse before you actually calculate whether or not you want to do it. If you can get the entire eigenvalue set, this actually works out to be the maximum eigenvalue over the minimum eigenvalue. And that's kind of a nice property. What that means is that your matrix transformation is stretching your function or your vector much more in one direction than another direction. And because you've got that kind of distorted thing, that's where the trouble kind of starts. Previous versions of this class didn't touch on iterative techniques very much. Condition number is very important to iterative techniques. I'm not sure whether or not we're going to be able to get to that without like just flooding you guys. The idea with iterative techniques is sometimes the matrix is messy. So then like there's a question, right? Like sometimes you will get a matrix that's poorly conditioned. So sorry, I should define that. Condition number equals 1, well conditioned. Anything off from 1, ill conditioned, poorly conditioned, not good conditioned, right? Any adjective of your choice, bad. Sometimes you're going to get them anyway, right? So what can you do? Do you have any ideas? Multiply by a, wouldn't multiply by number, I'll multiply by a what? A matrix. What you end up doing is you take your ax plus b and you multiply through by a new matrix P. So you get PAX is equal to PB. P is called precondition. And the goal of P is to make that new matrix product, that PA, have a better eigenspectrum, right? Which means that it has a better condition number. And like the whole of preconditioner engineering that's very, very necessary for iterative techniques is kind of concerned with how you determine P. And then you have all kind of optimization routines and everything like that go into that. Any questions before I go into the bonus head scratcher? That makes sense? Yeah. I'm gonna kick out some practice problems. I mean, there's a lot of Python tools and NumPy tools and SciPy tools too for calculating the difference matrix norms. I'm going to push some of them into here, and I think I'll go over them in the beginning of the next lecture, just so that you guys can kind of see and get your hands dirty a little bit. And then, surprise, surprise, it's going to be on the assignment, right? Like, and you can use those tools that kind of play with the different ideas of how to do it. Okay. Bonus time. I was reluctant. I was debating whether or not to put this up here, but I think you guys can. Don't worry about it, though. I'm not going to be testing you on this one. So I've already set it in. So original problem, 20, 50, 700, C plus T equals 20. let's add on another one. Let's say you have some other flimsy excuse for introducing another equation that is 50 times c plus 20 times t equals 700. Who knows what's going to happen? Nothing? What's that? Okay. What about the procedure that you're going to use to get this? Yeah. Anybody? Oh, definitely have to plot another line. What about the matrix? What about your matrix A? Yeah. You have more equations than you have unknowns, and that's termed an overdetermined system. It's very, very common especially in engineering. Oh, I forgot to mention something. Finish one thought before I go back. It's very, very common because a lot of times you'll have like two parameters and a whole bunch of data points. This is a rectangular matrix. That's what I was talking about at the beginning when I was on my rant. Yeah, I'm going to continue this and then I'll go back. When we plot it, we're going to see three lines and they still all intersect in a point. So this rectangular matrix actually does have an inverse. The inverse is called the pseudo inverse. There are different ways to calculate it, and we might actually have to fill in this gap because this is the way that you do fitting. This is the modern way that you do fitting, as opposed to other techniques. They amount to the same thing, but this is kind of the way that you do it. What is the determinant of a rectangular matrix? Nobody's learned that yet. Doesn't exist. Trick question. Gotcha. Which means that this whole formulation with like what a determinant is kind of limited, right? Because there we have a matrix that is invertible, despite the fact that it's not rectangular. And yet you can't even it's not even defined, right? So the way that you deal with that is called the rank of your matrix. The rank of your matrix is literally the number of independent, depends. You can have your column rank and your row rank. And what that means is that you can have some equations that you can solve, and the same equation is not solvable backwards. So the example there is, say you have an equation, you have two parameters and 100 data points, right? You can solve for x. You can solve for x. You can find your parameters, right? If you had 100 variables and only 2 data points, well, you could actually solve for that, right? But it would be a useless solution. You would have an infinitude of solutions, right? So this is kind of where it gets funny, because now you have a matrix that can be solved one way, but not the other. And that's where it kind of gets a little bit tricky. So hence the reluctance to kind of go down that rabbit hole. What do you think would happen, just to complete that thought, since we've still got 5 minutes, what do you think would happen if instead of 20, this was 21? What would happen to that line? It would move, yeah. Do you think the point of intersection would stay the same? Not at all, right? You would go. That's equally bad. I gotta use it. Right. This was your original solution. You would have a new line that looks something like that. And you now have 1, 2, 3 points of intersection. Can you solve something that has 3 points of intersection? No, right? Because now there are 3 places where they'll merge. What you can say, though, is that you can minimize the least squared error. So you can find the point here at which all those solutions are equally bad. Right? Which is actually what Amir was talking about. He was talking about the mean squared error. This is how you do that. This is how it comes out. It's from the pseudo inverse. That's how it's calculated, which is kind of neat. But again, I'm not sure if we're going to get there with that one. But feel free to look it up. It's pretty cool. Very quickly, what I forgot to mention before is with regards to condition numbers, the other problem with this, and it is in the notes, at least I wrote it down, is If you have something that's like a prescribed price, that's not so bad because now you know that it is exactly $20. It is exactly $50. In nature, you will never have exactly. You will always have uncertainty. And as soon as you get that uncertainty, if you have that very poor conditioning, now your result is going to be varying massively, depending on what the uncertainty is at that point. And this kind of like sinks us again, especially as engineers, right? Like we should at some point be standing in reality, and that's when that's when the condition number is kind of fun. Any questions? Excellent. Got 3 minutes extra. Look at that. Next class on Wednesday. Oh, sorry, one more thing. I forgot. Psych, gotcha. There is a AI lecture as part of the I think the John Hodgins lecture series. There's the director of, or the chair of the board of directors of OpenText, who's a McMaster grad, who is now all over AI and its kind of uses and things. It's on Wednesday, October 2nd at, I think from 4:30 is the reception, 5:30 starts the lecture. So I'm giving you guys a heads up. I'll send you the invitation, but we'll probably skip that lecture. That looks pretty cool. And instead come to the lecture and actually learn how it's related. Got it. You. I'm just gonna keep it in my backpack.
Hey, Dr. Willen, can you stop the recording real quick?
Yes.
Yeah.
How?
Good question. On more maybe, like if you click on the bottom of the top, it says more, record and transcribe. Does it say stop recording by any chance?
Aha.
There we go. Yeah, because it takes
the rest of your file. So you can do stuff like solve the matrix. I think I actually put this in. Oh no, it's one of the other ones, I think, where I literally say like I have a markdown where I'm actually like writing out a matrix, and then my prompt is solve the matrix above, and it does, which is honestly pretty impressive. But if you use a sidebar, I find that a bit more loopy. So I'm just gonna delete that. Alrighty. I already told you guys last time about the Gaussian elimination. I always have pronounced it Gaussian elimination, but everywhere that I'm reading when I'm pulling these together is all saying Gauss elimination. So I thought it was Gaussian elimination, and I'm probably going to say Gaussian elimination, but if you're looking it up, you'll probably find Gauss elimination. Anyway, first things first, we're going to talk about how to quantify the computational complexity of an algorithm. So it depends, of course, on the system that you're using, especially now if you're using HPC. Lots of different ways to do it, but the most fundamental way to look at it is count the number of operations. Even that part is complicated because now you get into things like vectorization. Right? And vectorization allows a single core to work on multiple different elements at the same time. So that even that gets a bit complicated, but we're going to do the best that we can. It's called Big O notation, and it actually ties back to the same formulation as we quantify the error, the approximation of the error. I did get the test results, and I saw that actually that was a bit of a weakness. So we're going to talk a little bit more about Big O notation and how that works. Okay, we're going to formalize how we, being you and me personally, when we look at an equation like this, how we would solve those equations. We're then going to transform that, or sorry, we're going to formalize that. We're going to work out how to put that into an algorithm, and then we're going to show how you get a normal linear system and make it simple enough that it becomes very easy to solve through Gaussian elimination. That's what it's all about. And then we're going to talk a little bit about pivoting and defining diagonal dominance, which sounds pretty cool. It's all right. It's very useful, but it sounds much cooler. Yeah. Okay, let's jump in. So I hate to read the slides directly, but here I am anyway. Computational complexity literally counts the number of operations. that way it's supposed to be free of hardware. There's kind of a problem if as soon as you start timing things, if you time things on different machines, obviously you're going to get different answers. If you time things on computer clusters where you're distributing these things, have you guys done any kind of distributed computing, by the way? You have. You're like programming in assembly in your free time. You don't count. Everybody else. Like, does distributed versus shared memory mean anything to you guys? Okay. That's fine because that means that I need to talk about it in context of some of these other algorithms and things. So kind of counting the operations is I would say the most abstract analytic way to compare these algorithms. That being said, the code that I have there is literally timing it, because counting the operations is actually kind of hard to do on a computer. There are some Python modules. Some of them are built in Google Colab, some aren't. But I actually got this nifty time it command here from the lab from Amir when he gave it. So I think that's pretty cool, and we can use that to kind of show our point here. Okay. There are a lot of things associated with an algorithm, and generally, if you count the number of operations, what we're going to do is we're going to quantify that with regards to the dimension of the linear object. So you have a vector of length n. You have a matrix of size n by n, or n by m, depending on how advanced you are with that sort of stuff. So what we're going to do is, the number of operations get something like n cubed divided by 8 plus n squared plus n ln n, blah, blah, blah. Forget everything past the leading term, right? We already talked about dominance. You want the leading term because that's what's going to dominate everything else when n goes to infinity. Are there any of you guys ever do sorting algorithms? Right? Complexity, this is kind of the way that you quantify the sorting efficiencies too. It's exactly the same thing. So, example, pop quiz. What is the computational complexity of, the answer's in the question. What do you think is the computational complexity of multiplying two n by n matrices? Right? So when you're multiplying, when you're doing matrix multiplication, you do row by column. That is n squared, right? Because you have to sum n times n. And then you do that over and over and over down the entire thing, and that's how you build it up, n cubed, right? They call this the school book algorithm for matrix multiplication. There are more efficient ones, which means, very importantly, the computational complexity is a property of the algorithm, not the mathematical operation. Okay? So, for example, there are other algorithms that have big O of 2.81. Sorry, that shouldn't be like that. That should be, talk about live demo. There you go. That's better, right? So let's actually time this and actually see it in action here. So what we're doing here, this is a super simple function for Python function. I just gave it the name, time, matmult, and it takes the dimension n, right? We're creating two random matrices, and then we're using this time it followed by this command. In Python, this, what do you call this? The @ symbol? Is that the actual name for the A? Well, ampersand is the other one, right? That's what I was about to say too, but I don't know what it's actually called. The @ symbol, right? That @ symbol, let's solve problems. What is called? Here we go. Demonstration. Attempting to reconnect. Demonstration failed. I told you about live demos. I literally told you. Okay, well, while Copilot is disappointing me, let's move on with our lives. This is shorthand for matrix multiplication, which is really nice. You can use it as an operator. Be careful, star is not matrix multiplication. I think star is actually element by element multiplication. I think we can verify that actually. Let's just do what are we doing here? Give me a second here. Another live demo. 2 by 2, 2 by 2. So anybody who is learning Python, feel free to question me on what I'm doing here. Print A, print B, print A times B. Okay, so here's one matrix. 8.6 times 6.2 is, well, what would that be? Bum, bum, bum. Anybody have a calculator? 0.86 times 0.62. Yeah, is 5.3. And that's that's approximately this element. So that multiplication is element by element multiplication. It's not matrix multiplication. So that's a little pitfall with that one. Okay, so this function just takes in the dimension, then churns through it and reports the time. This little percent sign time it just kind of like measures it, and it has an algorithm inside it where it repeats it a certain number of times and then spits out some stats. And then I do it for 100, 1,000, 2,000, and 4,000. Takes a little bit of time. Hopefully this one won't also die. The @ symbol. Okay. Copilot finally decided to join us. And apparently it is in fact the @ symbol. That's disappointing. The what? In the Python context, it's called a decorator. Yeah, but that's the Python context. I think this Gemini, are you using through Colab? Yeah, so that is specifically like it's pre-assuming that you're talking about Python, and that's a different function. It's kind of a more advanced function of Python. Yeah. Okay, so let's work out some math here. See how this is scaling. If we do n is 100, we get 1, 2, 3 microseconds. Let's call that 100 microseconds. If we do n 1,000, we get, let's call that 100 milliseconds. What's the scaling? Is that? I'm sorry? 10 to the power of 3, right? Pretty easy to calculate. This is using the timing is a little bit leery because you're timing the whole function execution, not just the matrix multiplication, but it's not bad. It still gives the right order of magnitude, right? So between 1,000 and 2,000, we've increased by a factor of 2. Between 100 elements and, between 100 milliseconds, 500 milliseconds, that's only a factor of 3. We would have expected a factor of 8, right? Between 2,000 and 4,000, we would expect, again, 8 because we've doubled it, but we actually get, what is that, 9, right? So it's not bulletproof. All this is like, it's all a mathematical approximation. That's why they say like, ignore the constants, ignore all the other terms around it. It's all about scaling, right? What this means is that what we're going to see is we can arrive at algorithms that solve these things in n squared time instead of n cubed time. And that's very, very useful. That's like a factor of 1,000,000, depending on the size of your problem. Does this make sense to everybody before I move on? Okay, good. Some complexities of common linear algebra operations are here. Oh yeah, I think you guys can read that. The matrix multiplication, again, that's the school book one. What are some other key ones? Matrix inversion is n cubed, as is determination, which is kind of funny, right? Because you might think that you want to do the determinant before you try and invert it. But actually, according to this, you may as well try and invert it and see whether or not it works. And if your algorithm just dies, then you skipped a step of calculating the determinant. Here it says the transpose is order n squared. I wouldn't have expected so because I expect like NumPy stores it as pointers. So instead of like moving, you guys know what the transpose is, yeah? You swap the rows and columns, right? If you have something that's indexed, all you would do is swap the index and now you have a transpose, right? That's like order 0, to be honest. So this is take this sort of stuff as kind of the back of your head. You're not going to be quizzed on this, right? This is just for your own knowledge. The matrix norm is order n squared. Hence, the norm is actually kind of more useful than the determinant. high performance computing introduces new elements of complexity. Basically, the key there is how you divide a problem. So no, okay. Guess what? I'm going to talk about high performance computing and the difference between shared and distributed memory. Okay. The way shared memory works, say you have 100 cores, right? You can buy a 100 core computer nowadays, AMD Ryzen, no problem. All of those cores can share your memory, which means that all of those 100 cores are working on the same matrix. So whenever you do something like you replace a vector, you do whatever, that entire thing can be moved into the cores, it's moved back, no problem. When you do stuff like high performance computing, you don't have that model anymore. Now you have one core with a block of memory. And over the network or whatever kind of connection, InfiniBand, you have another core that has a block of memory. And you have another core that has a block of memory. And it's like doing a group project where you're all working on like parts of the assignment yourself. And then you come together and you try and put it together into a report. Right? And it works terribly. Right? Like it's much more productive for everybody to be sitting around one table and working on something together. That's shared memory, shared paper, versus distributed memory. Everybody's going off doing their own thing, coming back. Okay. The problem is that a lot of these high performance computers are something like millions of, instead of cores, they use the term nodes. So a node is a box with a specific allocated memory. So each node could have one core. It could have 10 cores. It could have how many cores you want. But then there has to be a communication between nodes on this network, right? Literally network. So it's called scaling in high performance computing. And what you need to prove is that like when you go and you apply for time and you want to use all these supercomputers, you want to show that it's worth it. And what that means is that you have to show that your problem is going to be valuable. So if I had a problem and I could just run it on my laptop for twice as long, or I could move it on to the what I don't even remember what these guys are called. Titan, I think, at Argonne was a thing. I think it's now Aurora or something like that, right? If I could use the Aurora supercomputer and I could get 1 million cores on it, and it took almost the same amount of time, right? Like, no, I will be denied, right? So this is where you want to show the payoff, and that payoff is in terms of scaling. The gold standard is linear scaling. If you can show linear scaling, you're good. This is also, so Argonne National Labs has they call them leadership class supercomputers. They are probably actually bought for other reasons, but since they have those computers, they may as well use them for science. We'll talk about the politics later. Argonne also runs what I would consider to be like the main linear solver algorithm. They develop it. It's called PETSI. I forget what the acronym is. Portable Hierarchical Preconditioner Library, something, right? So this is why we want to use their linear solver algorithms, because they are specifically designed for million cores. And if we can say, hey, we're using this has already been proved to work on your supercomputer, then the people who decide the time allocation say, well, okay, go for it, right? So that's why we're doing this. Much harder said than done. Much easier said than done. I talk about that one ad nauseum later. Okay, so all that is a bit more of context. Do note that big O notation is again in a different. It's again being used. It's again the leading term, but it's being used in a different context. Big O is kind of all over the place. Okay. Gaussian elimination is the methodology, is like the algorithm form of what we would do naturally, to be honest, right? So what that means is when we go back to the question from 2 days ago, right? Chairs cost 20, tables cost 50, we have a budget of 700, 20 pieces of furniture total, right? The way that we would normally do that, if we're just kind of staring at it with our monkey brains, is to rearrange the second equation, right? First of all, write down your equations. Rearrange the second one. C is 20 minus t. Substitute that into the first equation, solve for t, and then substitute t into your choice of equation to solve for c. Okay, we're done. This works because we're carrying that unknown symbol. we're carrying a variable, that variable in this context being being t. And by algebraic or symbolic manipulation, that's how we're doing it. We want to do a numerical approach because that's only going to work, right? Like this works for a 2x2 pretty easily. It does theoretically work for 100 by 100. And if we're ambitious, we might actually see what that looks like here, depending on how the time goes. But like you can see this gets real ugly real fast. Okay. So the numerical approach says you write down these two equations, and instead of doing any kind of symbolic manipulation, you just multiply the second equation by 20. Now you get 20 plus 50t, 700, you guys can read, right? That's your other equation. You subtract the two equations, and you end up with 0c equals 0, hooray. And 30t is 300. This is trivial, right? We don't even need to solve this. At this point, the computer can take it. Okay, and then we do the substitution again for c. Now, here's the key. The system has changed. It is not the original 2050 11 720. We've now changed it to be something else. And that something else now looks like this. Here's the original equation, and we have 0, 30. And we've done that just by manipulation of that. Same system, same answer, different matrices. This type of matrix is something called upper triangular. Okay, note, important. Okay, it is the row echelon form for a single for a square matrix. If you guys remember, I think it's like second year linear algebra. You might have talked about like row echelon, reduced row echelon. Like this is the tie-in. The upper triangular is specific to square matrices, whereas row echelon, reduced row echelon is the more general. Okay, but we can look at it. We can see that looks like a triangle. Good. Engineering. Right? The answer is easily obtained through backward substitution, and it's actually obtained in n squared time. Right? So this is useful. If we can transform the original matrix, which normally we would solve in n cubed, into an upper triangular one, now we've benefited by a full order, right? Which is huge. If we're into like a million by a million matrices, going from n squared to n cubed to n squared, right? Big success. So upper triangular matrix in general is something that looks like this. Note the diagonal is filled, but there's nothing below it. Okay, surprise, surprise, there's also lower triangular that we'll see in a second, which is the opposite. Diagonal is filled, everything is below it, nothing is above it. It's all zeros. Okay, when we get an equation of this form, then it becomes super easy and solves very efficiently. This is the point of Gaussian elimination. That's the goal, to get to this upper triangular matrix, and then we can solve it real fast. Okay, so Gaussian elimination proceeds in two phases. The first is the transformation of AX equals B into this upper triangular form. The second phase is the back substitution, which we've already talked about is super easy. Okay, the way we do it, I'm going to preface this by saying that nobody actually does this. It's one of those things that like I have to talk about because everybody should know what Gaussian elimination is. It's only really useful for symbolic matrices because what we're going to figure out later is that actually A can always be decomposed into an upper and a lower triangular matrix in absence of the vector on the other side. I don't know if I'll get to that today. I doubt it. But that'll be what we talk about tomorrow, right? But nonetheless, I have to talk about Gaussian elimination because it's one of like the bedrocks, right? Okay, what we do, we build an augmented matrix, which means we take your B vector and you smack it on. You concatenate it, is the term. In NumPy, you can say, I think it's H stack, horizontal stack. In SymPy, that I'll actually show you guys today. I changed my mind. We are going to talk a little bit about SymPy because it shows you why you would never do this symbolically. You're going to see, I think it's called row join, i.e. you're joining in a row. I found that a little bit counterintuitive. I would have thought like a row join is like a join of two rows, so like a vertical stack, but nonetheless, it's called row join. Okay, we're allowed to do certain things on it. We're allowed to take the augmented matrix. We're allowed. Oh, not this again. I think we're back online. All right. I'm just putting this on here so that you guys can see what's happening with your with that coefficient matrix, that original coefficient matrix, right? You can multiply a row by a constant. This is my shorthand. You won't see this anywhere else. This is a mic thing. It's the chapter symbol, and I've just kind of used it. I like to use it as generic scalar. So wherever you see that, substitute in scalar of choice, right? I can't use A because all my matrices are A. I can't use X or Y or anything else. So I just use, okay. And what that does is it multiplies the determinant by the same scalar factor. You can subtract 2 rows, in which case you've left things unchanged. And that's it. That's all you're allowed to do. So this is complete disclosure. This is AI generated code. I don't know what happened to my prompt statement here. Whatever. It is anyway. Okay. So you've got the A matrix is from our original linear system, B matrix here, and we form the augmented matrix. So if anybody has any questions about the way this is being programmed, let me know. Okay. H stack, numpy H stack is smacking them together into the augmented matrix. And now I make this function that every time I ask it, it's going to print out what the augmented matrix is, what the determinant of A is. So you see that we're slicing this, right? If you guys remember slicing a matrix in Python, you do it with these colons, which means everything. So this is all rows and all columns up to the n minus 1. Right? Since B is a column vector, that means that we're separating out A. In hindsight, I should have just separated out A and then done all the calculations based on that, but I was lazy. And this AI generated anyway. Okay. Determinant of A, np, numpy, dot linalg, dot det. What do you think that does? Good. Norm, right? It's this easy. Okay, norm is not that easy because there are several different types of norm. So if you're in Collab, I actually think it gives you, here we go. It'll automatically pull up the documentation. It gives you different options for how to do these norms. Or you can use the SciPy. SciPy, so NumPy, number, Python, SciPy, science, Python. They're almost identical, but not quite. They are separated. I'm not actually sure why, they would bother to duplicate some of this stuff, but they do anyway. Okay, here are the options. Frobenius, nuclear norm. I was tempted to use that because I'm a nuclear guy. Blah, 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 and then you get your P norms and stuff like that. Doesn't matter. I mean, it does matter. You should be aware of that, right? Because if you do the norm using linalg and you do it using SciPy or NumPy and SciPy, maybe you're going to get different answers. That's the sort of thing you got to look at, right? And this is also the whole point of the course, right? Now you know that norms have options, right? And they depend on different types and blah, blah, blah. Okay. Let's hear. So what this is just kind of like a manual Gaussian elimination. This is not a package, and the reason is that there aren't any packages that do this anymore. I'll show you. Okay. So what we're doing is we're doing these row multiplications, subtraction operations, and when we run it, and it thinks about it for a second, here's the process. We get the original one. This is the original determinant. Example. 29.999999999, right? Case in point, round off error in action. You've got your norm, you've got your condition number. This condition number is being calculated. So again, there are different ways to calculate the condition number. This is the quote unquote proper way, which is the norm of A times the norm of A inverse. To which you say, which norm, right? And I would say something like Frobenius. Actually, I would look it up, right? Exercise for the student. When you multiply the second row by 20, sure enough, your determinant is multiplied by 20 the norm changes a little bit, and your condition number actually changes quite a lot. When you subtract them, you get another little change. I wanted to put in these because it shows that you can change these quantifications, these characterizations, the norm, the determinant, just by multiplying through by a constant, or subtracting, or even just moving rows around. I'll show you guys that one too. This is the basis for preconditioners, right? You can make a matrix easier for the numerics to solve just by multiplying through by a couple numbers, which is good. Which numbers? That's the hard part, and that's when you get into something like PET-C. Okay, let's work through the algorithm. The idea is that we're going to take our entire augmented matrix. We're going to pick a row. We're going to call it the pivot row. And I hate that they call it the pivot row because the pivot row is not the same as pivoting, which is actually the next section. So I don't know if like I'm missing the connection or the segue or what, but there it is. Okay, we pick the pivot row and we're going to use that to eliminate all the elements below it. So what we're going to do is we're going to say that the pivot is always the next one from the top. And we're going to eliminate any of those elements in the same column. So you start off with your equations here. This is a different example. Hooray, I got a different example. We turn it into ax equals y. We put it, y, b, that's the constant vector. Okay, you get your augmented matrix. So we're going to choose it as the first one. We're going to multiply the pivot row, the first row, by 0.5, and then use it to eliminate this pesky -2. We do that, and sure enough, we get a 0 here, right? And the algorithm, to be honest, kind of writes itself. You take that one, you also do it to eliminate the 0, the number below that one too. And at the end of the first pass, we've only got the 4 on the diagonal and nothing below it. We're working towards a triangular matrix. Right? We repeat that again, and because it's only a 3x3, we're actually done at this point. And what you get then is your upper triangular matrix, from which back substitution is trivial. Don't bother doing any more from here, just have it solve. Okay? The two phases of the Gaussian elimination is, here's where I go back on what I said about like big O notation. The number of operations is roughly n cubed over 3. Which means it's order n cubed, but we're actually going to need that n cubed over 3 in a second. The back substitution is n squared over 2. Actually, I wouldn't say this. I would say, I should have said, around, sorry. Okay. There we go. Order n squared. If we want to change this a little bit, so that's Gaussian elimination. That's the algorithm for Gaussian elimination. An obvious extension is instead of just moving from the pivot row down, we could do the entire matrix. So what that would mean is that for every diagonal element, we would eliminate not just the numbers below it, but also above it. Right? That gives us, and while we're at it, we can also just normalize it so that the diagonal elements are all 1. This is called Gauss-Jordan elimination. Very similar, just you're doing the pass instead of from pivot down, you're doing the entire thing, and it results in this. And this is super easy to calculate now because identity is its own inverse, right? So this is actually your solution vector. You're already done. You can skip the back substitution, right? So you would say, this is obviously more efficient, but Gauss-Jordan takes n cubed over 2 operations compared to Gauss elimination, which was n cubed over 3, therefore is more efficient when n goes to infinity. Right? This is why Gaussian elimination is kind of the go-to. It's actually LU decomposition, but Gaussian elimination is generally considered superior to Gauss-Jordan. Okay. Gaussian elimination is very fundamental, but it's basically been superseded in almost every case, to be honest, with the exception of symbolic logic. one of the reasons why it's been superseded, why I would say something like that, is because those decompositions, that LU decomposition, can be distributed. There are ways to do that. Whereas Gaussian elimination, you can't really. At every step, you need to know, like you're operating on the entire matrix at every step. And because you're operating on that, you can't, you take part of the matrix, you take part of the matrix, you take part of the matrix, let's get together afterwards. Okay. That is why I was not able to, not to say that you won't be able to, but I couldn't find a standard implementation of Gaussian elimination in NumPy or SciPy. Not there. I had to resort to SymPy. Symbolic Python. Good. SymPy is very similar to like Mathematica or Maple, if you guys have ever used that. There are a couple key elements here. I'm not really going to go into them. Feel free to poke around. It's pretty useful. I do like it for a lot of things. What this is this is defining a variable called A, right? Matrix, kind of self-explanatory. Let's see. I'm just going to put this in here. Oh, I know why I kept this here. Bum, 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 bum. Yes. I'm going to do a live demo. Generate with AI. I wanted to use the SymPy RREF and echelon to make an example for a linear system, right? RREF stands for reduced row echelon form. I think I forgot to mention that, didn't I? It's in the notes here. This is reduced row echelon form, right? It's ones on all the diagonals, nothing else. Okay. Gonna make that for a linear system. Go AI brain. And we get something that looks like this. Right? So here's an example of how we would see the reduced row and the row echelon form. That's how we would get it. Okay. Something nice if you are using SymPy. SymPy has this nice feature of P print here. P stands for pretty. So if you just ask it to print out that matrix, I'll show you. Print REF form 0, right? This is what it gives you naturally, and that's kind of ugly. So you want it to pretty print, and then it'll actually give you these nice features and show you something nice. Notice also something else with SymPy. It's using fractions. Is that what you're going to say? SymPy will still give you an answer, but in that case, it's going to have zeros. Yeah, I'll show you. Okay. I'm just going to can this one because I have this one already set up. So let me complete this one, and then I'll show you exactly what happens here. Okay, this is the exact same thing. So note that SymPy uses fractions. Very important. No round off error because it hasn't been done, right? The problem is here. So A is an unknown. Say I'm going to put A in one of my matrix elements, and I'm going to run it now. And now you start to see, all these things are being populated by these symbolic expressions. That's fine. That was just A in one place, right? If I do something like, I don't know, A squared, maybe A cubed over here. Oops. Funny thing with Python, the hat isn't power. You need ** for power. That's pretty common in programming languages. Okay. So now what you end up seeing is that you get these big long expressions in there. The length, the number of, let's see, I think the way it works is that the number of terms in that polynomial in here is n cubed. So what you're going to end up, so you actually have two. You have n cubed on top, I think it works out to be, and n cubed on the bottom. So you get these massive, massive expressions because you have 1 over the determinant. Determinant is a different n cubed. You have these massive polynomials. And when you get to live demo time, yeah. All right. I'm not going to do the live demo. Sorry, running out of time. When you get to bigger and bigger matrices, the length of those polynomials just gets massive, and it becomes too burdensome to actually still work with. Whereas if you're doing this in numerics, like it won't store that, right? It'll just add 2 numbers, subtract 2 numbers. So all good there. Okay. Any questions on that or how this is working? Python commands. Okay. So I've got 10 minutes here. Oh, you wanted to know what happens when you have a degenerate matrix, singular matrix. So a nice singular matrix is actually just this. And let's see what happens. So the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9 is actually singular, which is kind of funny. When you do the RREF, you get something that looks like that. So you can still do reduced row echelon form. This is the rectangular matrix, your augmented matrix, right? So it does still have RREF defined. I don't think you would consider this an upper triangular matrix at this point because it's not along those diagonals, right? And this is obviously nonsense, right? Because what this is saying is that one of your variables is equal to 0, which is also 1. Doesn't work. So good question. That's what you get. Pivoting in diagonal dominance. Sometimes the order of the equations matters for solving the linear system. It obviously doesn't, right? Like it can't. If I write whatever equation first, it's got to have the same solution. It shouldn't depend on that. But nonetheless, in these algorithms, it does. So a system with an augmented matrix, this will work with our scheme where we're identifying the pivot and moving downwards. This one won't. And this one won't because we have 0 out front. Okay. So the remedy here is kind of trivial, is just to swap 3 and 1. If element is 0, then swap. Okay. The problem is, this swapping can be accomplished using matrix algebra, using something called a permutation matrix. The reason why I have this in is that we're going to see that popping out. We're going to see NumPy is telling us what the permutation matrix is tomorrow. So I want to define what it is here. Permutation is super trivial. Basically, what you do is if you want to swap a row, you take your identity matrix. Everybody knows what the identity matrix is. Good. Easiest possible matrix with the exception of 0. And you just swap the rows in that. And when you multiply it, then you swap the rows on the other one. Okay. Diagonal dominance. The problem is a bit more insidious. It doesn't have to be 0. It can just be small. Because when you go through, you end up dividing. That algorithm divides by that small thing. And you're left with mixing magnitudes, right? Epsilon goes to 0. You get an infinity. And everything blows up in your face. Okay. So we actually don't want on the diagonal zeros or small numbers. So what we do is we define something called the diagonal dominance, which is this. That's a bit hard unless you're fluent in index notation. What it's saying is that the diagonal element is greater than, in absolute value, is greater than the sum of all the other elements on the row. Okay? And it's actually usually the case. For most situations that we're going to encounter in like engineering problems, this is true. Pop quiz, which one's diagonally dominant? Is this one diagonally dominant? No. Is this one diagonally dominant? Yes, right? The 4 kind of gives it away. There is also row dominant, or sorry, column dominant, but that's we're not going to get to that one. Okay. It can be shown that if a matrix is diagonally dominant, it will not benefit from pivoting, which is super nice because now we have a relatively cheap operation, right? And we can say whether or not we should pivot. This contributes generally, Mike, spelling, generally, to numerical stability. It's an issue with numerical stability, not just Gaussian elimination. This just kind of highlights it. The same thing with the determinant, right? Nobody does that, but it kind of highlights why that determinant is important. It contributes generally to stability and accuracy, and also convergence rate, even for iterative algorithms. So we're going to be coming back to this one. Matrix factorization methods, that's tomorrow, and efficient convergence. Okay, so I wrote it there. That's all I got. Questions? Comments? Queries? Okay. So, as I said, this is all nice as kind of background information, but honestly, we're going to do things differently. Is somebody texting me here? No, somebody's in the chat here. They have been speaking. Okay. Oh, that was at 5:28. Okay, thank you, Jason. Yeah, as I said, Gaussian elimination is kind of the basic way and kind of the way that humans do it. But really what we're going to be doing is decomposition techniques. One thing that we're going to be talking about tomorrow. So tomorrow we're going to be talking about a couple things. We're going to be doing decomposition. We're going to take those matrices and pull them apart to be a lot easier to solve. We're going to be talking about different types of matrices. Usually, so these matrices we would call dense because every single element is full. Normally, in most situations, we're going to have sparse matrices, which means that a significant fraction are going to be zero. Hopefully, it's actually going to be a sparse structure. So what we're going to see are things like banded matrices, where you have everything, all of your non-zero elements are located ideally on the diagonal, but probably like a couple parallel lines too. And you can kind of imagine where we're going with that one because that affects storage. For example, right now you don't need to solve a two-dimensional array. Now you can use other storage techniques. And that's useful. Again, like when you're thinking about this, we're kind of working with like 2 and 3D matrices. Think million by million, because that's when like numeric methods really start to carry their weight. Even some of the cases that we're going to get to are going to get over there. So that's it. Thanks for coming.
Thank you.
Thank you. Thanks for coming.
Have a good day.
Too. Let me. Huh. Linear systems 2. Okay, guys. No, still 1 minute. All right, 5:30. Let's start. So, goals of this lecture. I'm going to show you guys how to compute matrix decomposition. First of all, what that is. Second of all, how we actually compute it. We're going to apply some of those to the linear system so that you'll be able to see what's actually happening with that. And then we're going to touch on different matrix types and their decompositions. And finally, we'll finally come to the point where you don't want to invert a matrix. Never invert a matrix. Always just keep the factors. Finally, we'll find out why. So, commonly we have to repeat the linear solve for multiple constant vectors. The different scenarios for this are kind of abound, but just believe me when I say it's a very common thing that you want to keep doing this. You could take all of those constant vectors, if you knew them before, put them together and do Gaussian elimination on all of them simultaneously. That is a possibility, but generally speaking, you won't have the entire set. You'll have like one at a time and you'll have to do it in series. So what we want to do is we want to decompose the matrix into a form that's easier to solve. It's also very, very important for special matrix types that we're going to see later. And this is what all the optimized solvers are specifically designed for. In particular, banded sparse matrices. We'll touch on that. We've already seen this boost. We've already seen what happens with regards to back substitution. That's the where we have the ux is equal to b, and that solves in n squared time compared to a regular matrix, which is n cubed. So we've already seen that. That's where we're going for. In general, any square matrix, square invertible matrix, can be decomposed as LU. It is called LU decomposition. Very, very important. You guys will, if you're ever involved in numerics in the future, guaranteed you're going to see LU decomposition. Okay. L is lower triangular. U is upper triangular. Great. So the system becomes, from AX is equal to B, you get LUX is equal to B. And then what you're going to do is two different substitutions. First, you define this little middle equation, right? And then you get Ly is equal to B. You solve that for Y. You get that, and then you solve that for X, right? And what the benefit from that is that you get two order n squareds instead of one order n cubed. Again, think about n going to a million, billion, you know, the payoff is massive. Okay. L and U are not generally unique. So this is me getting your attention. The LU decomposition that you will get is not necessarily the LU decomposition that you will get. And it's not necessarily the LU decomposition that we'll see in a second. And there's actually very good reasons for this, but that's literally the next example. Okay. Dun, 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 dun. So how do we calculate this thing? Returning back to the previous example from from last week's course, not last week, yesterday. See where my brain is. Where is that long one? Here we go. Here's the example. So looking at this equation, you may have noticed a bit of odd nomenclature when we were deriving this, right? We kind of said, for example, that we took the pivot and we divided by this constant, M21, and then subtracted that from the second row, right? And then, so if you go back to the previous lecture and you take a look through that, you'll see like M31, M32. And you might have been scratching your head about why it was named that way. It's because of this. Those coefficients that you're multiplying the pivot row by, the first row, turn out to be the elements of your lower matrix. So just by doing Gaussian elimination, we identify U, but at the same time, we're actually also calculating L, which is really nice. The diagonal elements become 1, and this is your LU decomposition. Great. Let's just do a quick check. Here's the original matrix. Here's the matrices LU that I calculated there. And sure enough, when you multiply them out, you get the right array. Okay. Now we check what happens when you do the package, right? So SciPy and NumPy both have linear algebra packages. SciPy's is a bit more sophisticated. NumPy is a bit more, not brute force, but a bit more limited. SciPy has like different options for sparsity and things like that. I forget whether or not I talk about those. Well, I can just show you. So you can talk about any kind of permutation matrices. You can overwrite your matrices, which has efficiencies boosts. Again, especially for like large matrices, you don't necessarily want to be finding another block of memory like that. So you just overwrite it in place, which can be efficient. Yeah, there are some other options. So when we do this LU decomposition, note there are 3 matrices, right? And then you find the permutation matrix, lower triangular and upper triangular. And sure enough, when you multiply L and U together, you do not get the original matrix. But you know why? Right? This is the result from just multiplying L and U. 880 minus 2 minus 4, 5, 4, 3 minus 5. And what we wanted was this one. The difference is that the rows are swapped. The LU decomposition inside SciPy is doing that pivoting for you. And the way that you pivot, the way that you row swap is through that permutation matrix. So if you look at the permutation matrix, just a refresher from yesterday, what you do is you take the identity matrix and you just swap the rows on that. So this is not the identity matrix. Everybody knows what the identity matrix is, right? 1, 1, 1 along the diagonal, right? And this is swapped row 3 and row 1, no problem. Swapping the rows does not change the answer. Sure enough, if we apply PLU and calculate that, then we arrive back at the original answer. Yes. Yeah, no, that's fine. So reminder / take note. Usually when you use one of these packages, they will usually spit out 3 matrices, P, L, and U. That being said, nobody ever calls it PLU decomposition, even though it kind of is. It's always just LU decomposition. But that's why the lower and the upper triangular matrices aren't the same as what we calculated otherwise. Right? And that's just from row swapping. There are other reasons why you would also get that. Okay. Any questions about decomposition? Go on to the next one. Excellent. Making good time. Matrix types. LU decomposition has a lot of useful properties depending on the types of matrices. So beginning at the beginning, the 0 matrix is zeros. Any matrix minus itself is 0. Great. 0 is wonderful. When we can get it, everybody likes a 0. Next runner-up is identity matrix. AI is equal to A. Good. Diagonal matrix. This one is particularly useful. If you can get only elements on the diagonal, the inverse is just the reciprocal of those elements, which is very, very useful. Almost never the case. You're never realistically going to see that, except in like very special cases. Actually, we're going to talk about one of the special cases called LDU decomposition. Upper triangular, lower triangular. So I tried to put all this into a graph so that you guys have like a little table that you can look at in the future and go back and think, okay, that's what he's talking about there. Permutation matrix has a neat property that the transpose is equal to its inverse. So the P that the LU decomposition gave is the P that you're going to need to do PLU to calculate A. The decomposition, when it actually pivoted it actually multiplied through by the inverse, right? Because that's how it row swapped before pivoting, before pulling it apart, and then it reversed the operation. Luckily, P is classified as an orthogonal matrix, and that means that its inverse is also its transpose. Another common one is rotation matrix. You can imagine undoing a rotation is just rotating the other way, transpose. Okay. Next one is symmetric. Everybody know what a symmetric matrix is? The off diagonal elements are the same. Symmetric positive definite is a nice one. It's a little bit harder to understand, but it's also symmetric, obviously. The positive definite has this nice little definition, which to me is all gibberish. I can't understand that at all. What it is, think of a quadratic function in multiple dimensions. So if you think about a quadratic function that's concave, like that, now imagine a surface that's concave in all directions. That's a symmetric positive definite matrix. Okay? If you don't have it concave in all axes, then you have something called a saddle point problem because it looks like a saddle, right? But that's particularly relevant for optimization. Not sure if we're going to get to that. If we do, it's at the end of the term. Okay. Sparsity. Just raise your hand if I'm going too fast on this one. Okay. Sparsity. Sparsity refers to the fraction of non-zero elements in a matrix. It's if and usually there will be a significant number of zeros in your matrices, and it drastically reduces storage and computational requirements. Very, very important. Sparsity is basically your saving grace with all this. A lot, if not most, engineering problems have not just a lot of sparsity, but structured sparsity. And when you can structure your sparsity, then things become very efficient. We'll see. Typically, what you do is when you're looking to store these things, like for most matrices that we're doing, like 2 by 2, 3 by 3, it's nothing. When you go up to like 1,000,000 by 1,000,000, I think the largest I've ever done is 100 million by 100 million. Like you just get like storage weight, right? Like how do you even put that into your L2 cache, let alone RAM, right? With sparse matrices, though, there are more efficient ways to do it. So usually what you would do is you would imagine like a 2D array and you would just kind of populate those elements. But if most of them are 0, you don't want to do that, right? So there are different storage techniques that you can do. One is literally just one storage technique is literally a set of coordinates and the value, right? That's kind of an obvious one. You can also do a row and then a displacement along those rows. That's useful for banded matrices. I'm not going to go into them here because we're never going to use them. Like we're never going to play with them, with one exception in some of the examples. Just use the code that I'm using, right? And then you don't have to worry about it. By all means, go into it and look at it, but like we'll never have to visualize it, for example. We'll always convert it back to a dense matrix, which is the big one with all the zeros filled in to actually be able to see it. Okay. Regarding computation, if we can keep the sparsity while we're doing our computation, then our methods get very efficient. If we cannot do that, I'll show you the catastrophic problem. Then it's referred to as fill-in. Literally, you're filling in the zeros with non-zero elements, and it's generally regarded as a horrible thing. And if you start doing that, just find a better way. Okay. Sparsity patterns. You're going to see a lot of plots like this. Actually, no. If you get into this professionally and you really start to examine this, you're going to see a lot of plots like this. This is black wherever the element is non-zero. So you can see a few things here, right? First of all, very obvious is the diagonal. Typically, that diagonal is not just one pixel. It actually has a little bit on either side. Not in all cases. You can see that this is symmetric. Right? Symmetric problems are also pretty useful, pretty common in engineering. There's not much else that you can see. It looks a bit like a Rorschach type picture, like you can kind of see like a butterfly or something like that. It's useful to visualize what's going on with this sort of thing. Okay. Now we have already examples of sparse matrices, diagonal matrices. As I said, the inverse of a diagonal is also diagonal, which is very nice because then the sparsity is maintained, hence efficient. We've seen upper and lower triangular matrices, their importance. We're actually going to find out that the inverse of a triangular is also triangular. So the inverse of U is also an upper triangular matrix. Also very useful, not nearly as useful as banded matrices, which is the next topic. Look at that. Banded matrices only have non-zero elements parallel to the diagonal. Sometimes they're described by the term bandwidth. I've never really seen that term outside of a textbook, to be entirely honest, but let's talk about it here because why not? You're going to run into it in notes and the textbook. Tri-diagonal. Anyone want to take a stab at what that means? All right. Here's an example of a tri-diagonal matrix. Note how I'm constructing these. And by I mean Gemini, right? Because you're going to need this in the assignment. So half of this lecture is kind of like giving you guys the cheat sheet codes to get you like 50 or 60% of the way on your assignment. Now it's up to you to kind of fill in the segue and connect the different bits together. Okay. So what this is doing is it's literally filling the diagonal of this matrix T with the value 2 and 0 offset. So the 0 offset, this is like you would have to go in and read the documentation. And honestly, guys, like if you don't understand what the function means, take a look at the documentation rather than like playing with it and trying to figure it out, because that'll just make everything. You know what? No, let me go back a second. It's tempting if you don't understand something just to like kind of point and shoot, and like maybe you'll get the right answer, but the next time you come to that, you're just going to make the same mistake again. And you're just going to have to like point and shoot again. It's much more sustainable to actually go to the documentation and actually figure out what's going on and then solve the problem, because then next time you've actually progressed. You haven't just kind of figured out a solution, you figured out the whole solution. So collab is nice, and I think this is actually Jupyter in general that'll do this, but it'll pull up. Somebody confirm that one? Oh, yeah. So Colab at least does this. I think Jupyter does this too in general, but it'll pull up the documentation. So all you have to do is hover over it and you can see, okay, these are the functions that I'm looking for. Fill diagonal, A, ND array. Do you guys understand this this nomenclature, how to read something like that? Should I talk about it really quickly? I think I should talk about it really quickly. So Python function definition. Function name, argument number 1, right? ND array is a numpy array. Value is literally a value, so a scalar. And then you would have to read up what else the things are talking about here. This is the little blurb, and then it talks about what the different arguments are actually corresponding to. Note in this case, it gets modified in place, which is good to know, good to keep in your mind. Value is to write on the diagonal, right? No problem. Question? Yes. Yes. Yep. Yes. Thank you. Absolutely. So I'm just going to repeat that for the people online. The comment was that it also shows, so these are the input arguments, these are the outputs. And for this particular function, the output is none. Guess what none is? None is nothing. All right. That's why. So noting that it's being filled in place, that's why we declare this matrix of zeros, and then we modify it directly. Things that aren't modified in place, you would have to do like, and T is equal to blah, 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 fill diagonal. And then that new matrix is copied into T, but this is actually modified directly. And that's an efficiency thing, right? Okay. Offset is below and above the diagonal, right? So +1, because it's fill diagonal, you're assuming it's a diagonal, but is it above or below? That's +1 upper diagonal, -1 lower diagonal. Great. I don't believe it unless I can see it. Personally, I'm stubborn, right? Here is the dense matrix, and you can see main diagonal 2, off diagonals are -1 on both sides. Let's look at the sparsity pattern. Nice little matplotlib function here. Spy T gives me this. This is a tridiagonal matrix. Okay. Pentadiagonal. Pent means 5. Here's a pentadiagonal. The only place that I've ever seen a pentadiagonal matrix, no, let me go back a second. Tridiagonal is very useful. Do you guys remember talking about the numerical differentiation? And I talked about, yeah. Including the main diagonal and above. So sorry, the question was, what does upper diagonal mean? So yeah, I'm sorry. Upper diagonal in this context means above. Yeah. There you go. Okay. So the comment was that the labeling of upper and lower are actually reversed. And go AI. So I'm going to swap that one, and thank you very much for pointing that out. Okay. Yeah, so with the tridiagonal, the only place that the main place that I've seen that popping up is in numerical differentiation when you do central difference method. So in 1D, when you do the central difference, you take, if you want the derivative at this point, you take information from before and information afterwards and do the derivative like that. That means that you have before and afterwards in your ordered set. As soon as you get to two-dimensional, it becomes banded. You don't have this close grouping. Pentadiagonal is if you're doing a higher order approximation for your derivative. We can define some of those functions, but basically now you're taking two data points on either side. Pentadiagonal. Not very common. Much more common is the general banded matrix. That is literally, well, I mean, you can see it here, right? It's the diagonal a little bit and then other parallel lines to it. It forms the nice bands on either side. This is much more common. So you can imagine if you're doing a two-dimensional grid and now you're trying to do the derivative, right? You need the information from that side and that side. Maybe those are your tri-diagonal part, but then you also need the information above and below. And if every one of those grid points is in a vector and you've just kind of stacked it up, then that's going to form bands above and below. That's how it works. Even with a two-dimensional grid, you still make a vector of unknowns. And then those bands are defined by the geometry and the differentiation scheme, the stencil that you're using. Okay, block matrices. Block matrices look like this, which doesn't look very interesting at first until you realize that they're actually subblocks here. So this one, you can see the mouse there, right? This looks actually like a separate block by itself. Let's call that one A. This is D, that's the lower one. And then you have these off diagonals B and C. So you can actually, and in this case, A and D are the same. In general, they won't be. You actually don't technically need B and C to be square, but let's ignore that fact. Let's just say that they're square anyway and move on. Block inverse formula looks like this. You do not have to memorize it. What this means is that we can calculate the inverse of that block matrix by looking at the inverse of its blocks. And that's kind of useful, right? Because the block matrix, if it's dense, takes, but here, let's see. If each block is n by n, then your total matrix, the monolithic matrix, is 2n by 2n. Takes order 2n squared or 2n cubed to solve, right? As opposed to multiple n squared solves. In particular, it's useful when one of these blocks are 0. And that's actually also pretty common. Have you guys ever talked about Lagrange multipliers in the context of optimization? Anything like that? No? Okay. So optimization uses something called Lagrange multipliers, and that leads to a block where you have an entire block that's 0. So you can imagine what's going to happen if, for example, B or C is 0 here. All of a sudden, this entire term is knocked out. I'm going to come back to this one if there's time. Just note just one thing for me here. This term is actually the inverse of an inverse. Just keep that in the back of your mind for a second, and we'll come back to that one. Okay. The block matrix comes out a lot of times in multiphysics models. And we're going to talk, I don't know if we'll actually get to multiphysics in the context of PDEs for this analysis. But basically what you have, imagine your grid. Imagine you have two fields, temperature and concentration, right? Each field is going to have its own vector associated with those unknowns. So you have temperature, you have concentration, and you can imagine that block matrix, that system matrix, which encapsulate like heat transport, mass transport, is going to have a block structure. You're going to have one block that's describing Fourier heat transport. You're going to have another one that's describing Fickian diffusion, right? That's kind of where it becomes useful. Even more so when you have different types. So both heat and mass are both diffusive type. If you have something like heat and elasticity. Elasticity is an elliptic equation. It happens super fast. Generally speaking, we don't worry about like the time derivative of elasticity. It's actually a wave. Technically, temperature is also a wave, but nobody talks about that. But why that's nice is that then the different solvers work on different equations more or less efficiently. So you can do one particular solver for temperature, another solver for the elastic field, and then combine them. and that's pretty useful. If you guys ever run across a code out of the US called Moose or Bison, it's out of Idaho National Labs. They like to toot their horn about physics-based preconditioners. This is what they're talking about. What they're saying is elasticity works by geometric multigrid solvers. So we're going to use that for that. And we're going to combine that with a algebraic multigrid solver for temperature and bring those together. And that bringing together is through this block structure. Some people will call it operator splitting. You're splitting those two variables, keeping them separate, or segregated solving if you end up using COMSOL multiphysics. That's their terminology. If you solve the matrix as a whole, that's called a monolithic solve. Block diagonal is kind of neat. It also follows the diagonal matrix. So if both B and C, if your off diagonal blocks are 0, it actually turns out that, oops, this right? Your inverse turns out to be the inverse of the diagonals. There's a parallel that with a scalar case, and that makes it easy to remember. Okay, let's summarize some. Oh, geez, Mike, come on. I added something here, and now it and apparently I broke the table. There we go. That's better. Okay. Returning to matrix decomposition, and then we'll look at some examples. Any matrix, any square invertible matrix can be decomposed to LU. Don't forget that P in there too. That takes about n cubed over 3. A symmetric matrix can be decomposed into LDLT, which is kind of neat. So that's a lower triangular multiplied by a diagonal and the transpose of the same matrix, of the same L matrix. So you can imagine you immediately get a efficiency in memory storage is a big one, but also computation because you're exploiting that symmetric property. In the case where you have a symmetric positive definite, again, imagine a concave parabola in more than one dimension, then you can actually do LLT. It's called Cholesky decomposition, and it's basically the easiest, the most efficient one. Yeah, there's a little bit more involved in this one. What ends up happening between these two is that with Cholesky, you end up taking a square root, which is why it doesn't really work when you have just a general symmetric. It only works when you have a symmetric positive definite. That square root ends up being related to the curvature. So for a positive curvature, you can do square root of a positive number. For the general case, it might be negative, and then we're into complex, and nobody wants to go there. Some of the textbooks will take you through the different algorithms for calculating these. Cholesky and LDLT decomposition, LU decomposition. By all means, take a look at them if you really want. I didn't see any value covering them in this course because I would never suggest that you actually program one yourself. There are packages for this, and they're better ones. And I'll talk about those packages in a second. Okay. In general, this is a nice little matrix inverse equation in general. A inverse, the inverse of a product of matrices is equal to the product of the inverse of those matrices, which is to say LU inverse is equal to U inverse L inverse. Order is swapped. Okay? It would be tempting to store A inverse. Usually what's going to happen when you're running these sorts of systems, it's going to say matrix factorization. That's actually like the bulk of your time spent. It's going to be a matrix factorization, and then it holds on to it. And then it actually does it. And then it actually like solves the equation. But you're actually storing L and U. Even though you could calculate A inverse, we'll see why. First of all, inverse of a triangular matrix is triangular. This is just a nice little demo. When you run this, oops. Yeah, So when you run this, you're just going to see that, yes, in fact, the inverse of an upper triangular remains upper triangular. Great. LU decomposition of a banded matrix is banded triangular. This is where things start to get interesting, right? If A itself is banded and then you decompose, what you're going to get is, well, this is for Cholesky, but the same thing is true for LU. Your diagonal matrix here is also banded. And that's very useful. This is for, let's see, that's for the pentadiagonal one. But it's also true in general for the banded matrices, right? So here's where we're taking that efficiency from the banded structure and we're propagating it. We're holding on to it when we do that decomposition. This is how the Cholesky algorithm works, by the way. You can just run it, or you can look up how it works. Okay, here it is. Inverse of a banded matrix is not banded, with one notable exception being the diagonal band. If you only have the diagonal, then you maintain the banding. This is a bit disturbing, to be honest. Oh no! What happened? Ought not to find. What the? Oh. Yeah, sorry, it's because I just ran this one separately. There we go. Okay, this is my tri-diagonal. It's the simplest of the bands. That's not just the diagonal. Guess what happens when we invert it? Black screen of death. The inverse of the simplest one is completely filled. If you look at the inverse, you see that it's non-zero everywhere. This is why we don't store A inverse. Breaking it up into the factors L and U, those are nicely banded, right? And they're very sparse. The sparsity pattern is maintained, but the inverse is terrible. The other reason why you don't do that is also because of that determinant. When you do the determinant, unless you are very well conditioned, you run risks of round-off error. So by storing the factors directly themselves, you also don't have to worry about that. It's a more robust solve to do it that way. Okay, package implementation. Both of them do, both NumPy and SciPy do LU decomposition. That looks funny. I think I missed, I think I've got an extra O in there. Composition. Okay, and then the solution. In general, they can be accessed through linalg, solve. That's the linear solver. It's the same thing to get to the LU decomposition. You just do LU instead of solve. When you're looking at the options of the SciPy one, you can see that you can specify the matrix type. So I'm not sure if it has an internal check. Probably for the sake of efficiency, I don't know, actually. I don't know if it would or not, but you can tell it, hey, this is a positive matrix. This is a symmetric matrix. Hermitian is positive symmetric definite in this context for real matrices. Okay. And then you can also give it the options to overwrite and do the matrix computation in place, which saves the memory. So with the advent of HPCs and distributed computing, there was a big surge in developing these different algorithms, and these are kind of the main ones that you're going to encounter out there. Also trilinos, by the way, I don't think I included that one. The big one that you're going to see a lot of is UMFPAC, unsymmetric pattern multifrontal method. We're not going to talk about what these multifrontal methods do. I think I did describe them yesterday, right? Like the whole idea is that you build the big matrix from little matrices. So if you have a big matrix like this, you can build it from over here, you expand, this is your front, this is your moving front as it moves through. But because it's multifrontal, you can also start down here and build your front that way. And then you can overlap and you can get to your result. Right? That's the super simple, i.e. the one that I can wrap my head around, way of like how these multifrontal methods work. Mumps is another big one. It has the word massively in there, so everybody thinks that it must be better. Paradiso is actually, in my experience, so Paradiso and Super LU are both, they use a different technique. I have no idea about it. Google it. Absolutely no idea. Something about super nodes. SciPy actually has Super LU built into it, so you can access it right away, which is kind of nice. Unpack, Mumps, and Paradiso are both are all, you have to import that. If you do want to play around with that, you can actually ask Gemini to give you the code, and then it'll tell you how to bring it into the Google Colab environment, which is kind of nice if you want to play with it. Okay. So this is just, yeah. I don't think I really need to run this. Just an example of how you do the solves. Assignment. This is how you do the solves, right? And then we get to this one. We are solving so I wanted to solve a 200 by 200 sparse system with sparse solvers and then again with a dense solver to see the difference here. And we're using the, what's going on now? So I never do demos. What are you talking about? X sparse is not defined. It's right here. What? I'm just gonna reload the notebook if this doesn't work. Yeah, but then it doesn't tell the thing. Yeah, but it should. X sparse is not defined. Print solution using sparse solver. Right there.
Is A sparse defined? I see it commented out above. Oh, above.
Where is that?
Never mind. I just saw a commented version on the
Oh
screen.
yeah. I changed the way that it was defined in there, but it shouldn't have broken anything. I don't understand what's wrong here. Well, yeah, I know, eh? So these lines were just spitting out the solution anyway. So let's just try and see if we can get the timers. Yeah, there we go. Okay. So sparse solver takes, what is that, 300 microseconds. The dense solver takes 1.3 milliseconds. Note how this code works. Assignment, hint, hint, nudge, nudge, right? Just take this and modify accordingly, right? We've already showed you how to modify that previously. Look in the previous lectures. And we can play with this. So already you see there's a big performance enhancement, which is what this game is all about in this case. These particular sparse solvers, this is all working on banded matrices. Banded matrices, you know, they come out a lot with finite difference schemes because of the stencil for the derivatives. The modern way to do things is using the finite element method, and for that the sparsity looks, you know, like this Rorschach image up here. So the performance increase won't be as drastic as it is for the banded matrices, but we can still play around with it and take a look. Okay. General tips for doing this sort of thing. First of all, direct solvers are your black box for most of your needs. They're going to be your default, and 9 times out of 10, if not 99 out of 100, it's going to work. They're by far the most robust. They even work for ill-conditioned systems, which are great. You don't have to worry about that. They scale terribly, absolutely horrendously. They'll get up big, and at some point, you're going to run out of RAM on your computer. So you're going to beg your supervisor to get you more RAM, and you're going to be able to increase your problem size by like 5%, and then you're going to be into the same problem again. They also scale terribly in terms of parallelization. So even just like if you go to one of these supercomputing clusters and say, I want to do LU on your supercomputer, they're going to laugh at you. Like the answer is going to be no. Got a question? I think 50,000 by 50,000, a 50,000 by 50,000 matrix tops out about 10 gigs. And 50,000 is not a large number, no, for this sort of stuff. Your computation time at that point, I think George's was around 8 hours for computing this, and like that's really bad, to be honest, for that scale of problem. If you do use them, because you will use them, do start with a small system and work your way up. I don't know, I doubt we're going to get into geometric multigrid solvers. That's like kind of the modern paradigm with it, and that uses like a small linear, a small direct solve, LU solve, right at the beginning to get everything else started, and that works really well. But it only works because you can do the small solve. If you do get a code and you start to play around with these techniques, don't expect to see a speed up with an increasing number of nodes until you get to like above 10. Generally speaking, anything below 10, like the overhead of communicating between these distributed systems, is going to dwarf whatever computational speed up you get. Okay. The rule of thumb that I got from Argonne, by the way, was 10,000 by 10,000. Anything beyond 10,000 by 10,000 on a single LU solve, don't bother. So even just the difference between 10,000 and 50,000, like you start to see where that's going. Some implementations, i.e. NumPy, are smart enough and sophisticated enough that they'll solve even though your matrix is singular. In which case, what it's actually doing is that funny pseudo inverse thing, and it's doing a least squares answer. It is not a unique answer. And you just kind of have to be aware of that one. Sparse matrices are your saving grace. Do your best to protect them. Hence, don't use your inverses.